So this is the second video, and in the previous video I developed the Lagrangian for the quantum electrodynamic case. In this video I'm going to develop Lagrangian for the quantum chromodynamics. Okay, so let's start from the fact that in quantum electrodynamics we used psi, which was a spinner. It was representing, let's say, alpha and beta. It was representing a fermion, and here we will use Q. Q represents actually it's a color space, so Q is for quarks, and we will have three colors: Q red, Q blue, and Q green. Yeah, okay, sorry about this sloppy writing or sloppy notations, whatever. Okay, so we will work in the color space, and quarks come in three different colors, and Y3 because there is experimental evidence for the colors to be three. I'm not going into that detail because right now I will just do a little prerequisites for the Lagrangian of quantum chromodynamics. Okay, so we have three number of colors, and then yeah, there will be three anti-colors: Q green. Okay, so we will start from the fact that at high energies, let's say asymptotic freedom, freedom, we can write our Lagrangian for free quark. Okay, so it will be same like before, but we are no more in a fermionic field. Now we are in quarks color space, and in QED we used psi, which was representing spinors. Here we are using Qs, which are representing the colors, the three color states. Okay, now we see that how our Q space or Q color space transforms. So the transformation rule for Q is it transforms like this, and for Q bar it will transform like this. Yeah, okay, so one thing to know is that, not a one thing, there will be more than one things, but in QED we were working with U1 group, U1 phase transformations, and U1 is commutative. But here in case of QCD we are working in spatial unitary group SU3, basically SUN in general, but since we have three colors, so yeah, SU3, and we will be working in SU3 group, which is non-abelian. Yeah. On the other hand, if we look at QED case U1 unitary group, that is abelian. Good, we are having no problems, I mean less problems in QD case, but in case of QCD we will have some problems, but with those problems we will have some very beautiful things at the end. Yeah, no pain no gain. So yeah, with this non-abelian nature of QCD we will get some very beautiful results at the end. Okay, so let's talk about this unitarity operator. So this unitarity operator follows some rules. That is equal to unity, and further this also holds for U, unitarity operator. Determinant of U will be 1 and trace of U is 0, and it will have this form: U is equal to e to the iota ta theta of a. Okay, ta, we will see that these will be the generators of this group. It will have this form, later we will see, and lambdas of a will be called the Gell-Mann matrices. Yeah, there will be 8 generators. So about A, yeah, the A in the subscript that I'm using. So these are the generators of SUN symmetry. So yeah, in this case, because we are working in the color space, and so yeah, there are basically n square minus 1 number of generators, and in our case that will be 8. So yeah, 8 number of generators. Okay. Now moving forward, let's make this clear that since these are non-abelian, so the commutation relation between these generators is equal to iota FABC T of C, where FABC are the structure constants. Yeah, and more about the structure constants is that they are real and they are anti-symmetric. Yeah, they will be anti-symmetric with respect to each index exchange. Okay, So more about these generators is their Hermitian. So TA is equal to TA dagger, and yeah, TA is equal to lambda A over 2, and as I said that for since we are in SU3 symmetry, so A runs from 1 to 8. So let's see what are lambdas of A. Lambdas of A are Gell-Mann matrices. So I'm going to write down these matrices here. So I'm going to do it quickly. Okay, so I was going to write them all, but then I thought, why not take a picture and paste it here. Okay, so these are lambdas of A. These are the Gell-Mann matrices. Let's move on. Okay, now let's go back to our Lagrangian, and now we are going to check that if this Lagrangian is invariant under global phase transformation, and then we will check for its invariance under local phase transformation. So let's first check that is this Lagrangian invariant under global phase transformation. Let's see. So let's write the transformed Lagrangian. Okay, so yeah, let's write it here. So Q bar transforms like U dagger Q bar, and then I can write iota gamma mu d mu minus m. Let's write Q here and U here. Q prime transforms as U. Q prime transforms as U Q bar. So okay, so if we look, carefully, then gamma mu d mu minus m q, sorry, this might confuse. Okay, I am okay. So yeah, since U into U dagger equals to 1 equals to unity, as I have mentioned earlier, so it's equal to Q bar iota gamma mu d mu minus m into Q. So yeah, so this Lagrangian is trivially invariant under the global phase transformation. Now moving forward, so yeah, it's invariant. Okay, now let's move on, and let's say that u is a function of 4 position, and let's see that if so if we write this, it will be like this: d mu of u. Okay, problem, this term right here is breaking the symmetry, or we can say that it's breaking our balls, as my friend would say. Okay, now comment on this, why Why this this is a problem? So the fact that when we are doing local transformation, we are getting an extra term which makes our Lagrangian variant, means it's changing under the transformation, or yeah, so, or we can say that this extra term is breaking the symmetry of our Lagrangian, or makes our Lagrangian invariant. So yeah, this is a problem, and we need to solve this problem. And luckily we can do the same thing. I mean, we can apply the same formula that we did apply in QED case by introducing mighty, sorry, that's not a physics term, by introducing covariant derivative. So covariant derivative is going to solve the problem, and in this case our covariant derivative will have this form: unity d mu plus iota g of s g mu. And yeah, g of small g of s represents something that we will later find, find that this represents the strength of interaction, yeah, coupling constant gs, and g mu's will later be the gluon fields. But yeah, let's not, because we are going to build Lagrangian and see its mathematics, because yeah, that's what I'm interested in right now. And yeah, if you want to relate things, then relate things with QED, that then we can relate GS with E of QED, and we can relate G mu with A mu of QED. Yeah, now let's move on. Now we can now check that if this covariant derivative transforms as our field transforms. So yeah, we are going to see a proof that whether this covariant derivative really works or not. Yeah, let's move on. Okay, so let's see the transformed version of this. So we plug in the unity, and by manipulating this we get q prime, because q prime transforms like this. And by doing this we see that d mu prime version of d mu is u d mu u dagger. Okay, now let's move on to the real calculation. So okay, I'm going to write d mu is equal to g mu, and now if we write its transformed version, so using this thing right here, we can write this like this. Yeah. So okay, so all of a sudden I started using the upper transcript. So yeah, let's from now on I'm going to use the upper transcripts to make a distinction. GS G mu of u dagger. Okay, so this thing right here is simply d mu plus iota g of s g prime of mu, because we're writing the transformed version. Sorry. So yeah, about this, these are operators. So I'm going to use the chain rule here and write them like this. And then the last term, you take it. Okay, about this term will be equal to 0, and so this term is unity. U Taker is equal to unity, and eventually we will have d mu plus iota gs g prime of mu. We have to better simplify things a little bit. I'm going to divide every terms in this equation by iota gs. So I will have minus iota g of s, sorry, yeah, dividing by iota g of s. Let's write it here, u or u dagger plus d mu divided by iota g of s plus, yeah, if we divide by this term, then mu u dagger. Okay, so these two terms will vanish, and at the end I will have something. Okay, I'm going to do a little manipulation here, multiplying by iota and dividing by iota. So I will get a minus iota divided by gs u d mu u dagger plus u g mu u dagger. Okay, now if we take this, let's write it with a different color. No, let's use this color. Yeah, if we take this, so we can simplify this by doing u d mu of, you can write it like d mu of u into u dagger minus d mu of u into u dagger, and so this will be nothing but unity minus d mu of u into u bar. So yeah, this will go to 0, and eventually we will get our mu prime of g equal to u g mu into u dagger plus iota upon gs, because this minus with this minus will give us a plus, and we will have a u mu d mu u into u dagger. So this is how our field transforms, and a similar thing we also saw in QED case. Anyway, field does also transforms as the covariant derivative transforms, and we can also write g mu, which is a field, in terms of fundamental representation of SU3 algebra. So yeah, we can write this G mu in fundamental representation. Let's write it like that. So G mu for beta is equal to 1 upon 2 lambdas of A of alpha beta G mu A and x, since we are writing x because we are going for the local transformation. Here alpha and beta are color indices and mu goes from 1 to 4. These are Lorentz indices, and A goes from 1 to 8, and these are the 8 gluon. These will be the 8 gluon fields. And yeah, this term right here, let's highlight it. This is the representation of gluon fields in terms of its components. Let's move on. Okay, so now we're going to write an infinitesimal transformation in color space. And if we remember, we have already written that we can write U like this. So yeah, I'm going to, let's say, copy it from here and paste it here just in order to remember. Okay, so so what I'm going to write is the infinitesimal transformation in color space. So this is our transformation rule, and we can write U like this: unity plus iota lambdas of A divided by 2 delta theta A plus some higher order terms, Okay, now we are going to apply this transformation, and let's see how things work out. So we can rewrite this as very bad, lambda A divided by 2 delta thetas of A, and for Q bar we can write like this: 1 minus iota lambda A divided by 2 delta thetas of A. So this is the transformation. And now let's see how we can write an infinitesimal variation in the color field. That will be nothing but this. So this will be, yeah, we can also do calculations for this. Identity plus iota lambdas of A delta theta A QA minus QA, and that will be nothing but this iota delta thetas of A lambda A upon 2. I'm writing it in components form. So g of mu which was our auxiliary field in QCD case, the primed version can be written like this: g mu of u dagger u g mu u dagger. For this we can write so it will be 1 plus iota lambda A by 2 delta theta A g, and g mu we are writing g mu, so g mu can be written like this in components form: lambda A divided by 2 u of g mu p. So lambda A divided by 2 g mu of p into u dagger, which is 1 minus iota lambda A divided by 2 delta theta of A. Okay, so when we multiply and do the mathematics, we will get some terms in okay, let's do this. The video is getting longer, but anyway, no problem, we can do this. Lambda A divided by 2 g mu of p plus iota lambda A divided by 2 lambda p divided by 2 delta theta A delta theta A into g mu of p multiplied with this expression right here. So I have to use A, B and C to make the distinction. Divided by 2 g mu of p minus iota lambda p divided by 2 lambda c divided by 2 delta theta c g mu of p plus iota lambda A divided by 2 lambda b divided by 2 delta theta of A g mu p plus, then there will be lambda A lambda b lambda c divided by 2 to 2, that will become 8, and then there will be 3 theta terms. Okay, so I'm going to call these with, okay, there is also a g mu of p, so this term is higher order terms of theta, so that will be negligible, small, so it will go to 0. So eventually I will get u g mu into u bar as g mu plus iota delta thetas of A delta A divided by 2 lambda A divided by 2 lambda B divided by 2 minus lambda B lambda C into g mu of B, and this is a commutation relationship which can be written as commutation between lambda a divided by 2 lambda b divided by 2 of g mu b. And this is all due to the non-abelianity non-abelian nature of SU3. Okay, so if we recall that I have introduced the structure constants, and the commutation relation was something like that. Structure constant times. Okay, so here I can write here, this can be written, this commutation relation can be written in terms of this structure constant. So there is iota here and iota here, that will give us a minus FABC of lambda c divided by 2 g mu c. So yeah, so this t's of c, and we can write this like lambda c over 2 into g mu of c in components form times delta theta a. So this right here is the ug mu into u dagger. So this comes from here. So here was, yeah, so this is the part that we solved right now. Now we will move on to this part. Let's move on. Okay, for d mu u into u dagger, which was the other term that we are going to solve right now. Okay, so we can write this as u can be written as an infinitesimal transformation in the color space like this, delta of theta a into u dagger, which can be written as identity minus iota lambdas of b into delta theta b. And yeah, I'm just going to write the result, because the derivative of identity will be just 0. And if you do the math, so okay, so we will get a term with second order in delta thetas that will be negligible. So eventually d mu into u dagger will be equal to iota lambda a divided by 2 and d mu of delta theta a. So finally, now if we write this term and this term all together, so the transformed field can be written as g mu of a minus iota f a b c, which is the structure constant, delta theta a g mu of a minus 1 upon g of s d mu delta theta a. Okay, now let's talk about this So the transformation of the field here does depend on field itself, and this is a consequence of non-abelianity of SU3 group. If we compare it with the quantum electrodynamics case, so in QED we have not seen anything like this, because U1 group which governs the dynamics of QED is abelian, and due to the abelian nature of U1 group, that is the QED case, photons do not have any self-interaction terms. But here, due to the non-abelian nature of SU3 group, we are seeing the self-interaction terms among the field itself. So yeah, gluons are going, yeah, this field is the gluon field, and yeah, gluons are going to self-interact, which we did not see in case of QED. Another thing is that in case of QED there was a Q parameter which was characterizing in QED, in case of QED we had a Q parameter which was characterizing the charge of fermionic field, but in QCD case we have not yet introduced anything like that of Q. Actually, the non-abelian nature of QCD is not fixing the charge, so we can have any value for the charge. So yeah, so QCD does not fix the charge of fermions like it was in QED case. So theory has this theory, QCD theory, has not any restrictions on the charge. It can be 1, 2/3, 1/3, whatever. Okay, so far we have seen that the variation of the field, gluon field, depends on gluons itself. So the field depends on field itself, number one. And second, we have seen GS, which looks like, I mean, so far it's like a universal interaction, which will give us the strength of interaction among the fields, and there are no amounts of color charge. Now moving forward, we want to get a kinetic energy term for our G mu field. So we are going to get a kinetic energy term for G mu field. And for that we are going to use a commutator of d mu. Let's do the math. So we need commutator of g mu nu of this shape, d mu, and that will be nothing but this. Okay, we have this, so we need this and this. So first I'm going to write the equation for these two things right here, and then I'm going to put them in this commutator in order to get a kinetic energy term. So yeah, let's start. Applied on Q, and it can be written as d mu plus iota gs g mu into d nu plus iota gs g nu, and I'm going to multiply it. I'm going to pause here. So this is the multiplication. We can do the same thing with d nu d mu. Okay, so here's the result. Now if we look at the third term here and the last term here, similarly here the third and the last term, these two terms in each of the equation are not symmetric. So we are going to put these two here, and the symmetric terms would cancel out, and the terms which are not symmetric will be the only one left behind. Let's see. Okay, so we take the common term out, so we will be left with d mu g mu d mu g mu minus gs square upon I g mu g nu minus d nu g mu plus gs square upon I g nu g mu, and at the end we are going to get d mu g mu yes, iota square will be minus 1 and then minus, and this gs will cancel out, and here we will get d mu, this term d nu g mu plus gs, one of the gs from here will cancel out, and we will get gs, and g mu g nu minus g mu g mu, and this is a commutator which is equal to, I'm writing with a different color, iota g mu, commutator of g mu g nu. Okay, bad writing. Okay, so eventually d mu g mu, and if I write in d mu g mu plus iota gs, and iota comes from the commutator relationship g mu g nu, and yeah, let's write this in b a is, and there will be b's and c's in the, okay, so this is in the component form. So yeah, similarly if we write for g mu g nu, so So it will be d nu d mu of A minus d nu g mu of A plus iota gs g mu of B g nu of C. Okay, but we know that this can be written in terms of structure constants. So g mu of B, g mu of C, and similarly for the other. Okay, sorry, I have already used the B's and C, so I'm going to use D and E. So yeah, now the kinetic energy term will have this shape, trace of g mu nu, which we already evaluated, and trace of g mu nu is equal to half of the g mu nu A g mu nu A. Okay, so Lagrangian kinetic energy term of the Lagrangian will be minus 1 upon 4 g mu nu 1 upon 4 d nu g mu of A, yes, and d nu g of A, g mu of A, gs g mu of A, g mu of B, sorry, A's are already, so B and C, this multiplied by this term, which is d mu g mu minus d nu g mu plus iota gs d mu of d g mu of d g nu of E. Yes, okay. So we are going to get so this is a kinetic energy term. Building on that, and now I'm going to write the commutator relation in terms of structure constants. So let's see. D mu g mu of A minus d nu g mu of A, and if I use this relation right here, iotas will give me a minus gs f a b c of g mu g nu c. Similarly, for the other term, I can write g nu minus t nu g mu gs f a d e. Okay, g nu of t, g mu of t, and g nu of e. Okay, so now what I'm going to do, I'm going to multiply these two and see what I'm getting. Okay, so after multiplying, I get a quadratic term here, this term, this, and then this term. Okay, so moving on, simplifying a little more. Okay, so by using this property of the structure constants, we can add this term right here with this term right here, so we get a factor of 2 twice, and yeah, now we move on. Let's see. So now multiplying also -1 inside, we get d nu g mu of a minus this vector gs, and there will be -4 multiplying with these two terms, and the fact that we are adding this term and this term and using this property, so we get a factor of 2. So eventually multiplying it with 1/4 gives us gs upon 2 d mu g mu of a minus d nu g mu of, okay, f a b c. Now using that property, g mu of b, g mu of c plus g, now the term with the gs square, and multiplying -1/4 will give us a b c f a d e. Okay, there is a mistake of sign here, it should be minus, because yeah, and there will be okay, and we have 4 gluons, so I'm going to write here g mu b, g nu of c, g nu of d, g mu, and g nu of e. Okay, yes, okay, this was plus, this was minus, and yeah, this was minus here, so it will become plus. First term will be minus with the minus sign, and second term with the plus sign, and the third term with the minus sign. Okay, so far so good. Okay, so this is the complete kinetic energy term, and we are seeing uh, some 3 gluon interactions and 4 gluon interactions. So this term right here is the 4 gluons interaction, and yeah, 3 gluons interaction term. Okay, so I forgot to put a square here. So gluon interaction, 3 gluon interaction and 4 gluon interaction. Okay, now before moving forward, we can write a mass term here, which will be quadratic in nature. So we can write that like this: the mass term, mass of the gluon, mass of the gluon times g mu a g mu a. Okay, so due to the gauge principle or the gauge theory, this theory, I mean the gauge theory, constrains us to have massless gluons and the massless photons helped us. I mean, the gauge theory demands, or it requires, that the bosons must be massless, and it was helpful in case of QED, and the fact that experimentally the gluons are found to be massless. So yeah, here the gluons are also massless, so no mass term. So win-win situation for us. So no problem, for no worries for the mass of gluons or the gluon, the massive gluon term in the Lagrangian. So now that we have the kinetic energy term, we can write the full Lagrangian of QCD. Okay, so the things were a little messy so far. So just a quick reminder that from where we started and how we developed our Lagrangian so far. So basically we started from Dirac free Lagrangian, and we used a covariant derivative in order to preserve the local transformations, and then we got the gamma mu d nu plus iota gs g mu minus m q a q bar a. I'm just going to write down the result: iota gamma mu d mu minus m q minus gs divided by 2 g mu of a, and yeah, summation sign is compulsory under the alpha beta gamma mu q mu b. So this was the starting point, and we get self-interaction terms. This is the Dirac free Lagrangian. So okay, so now if we want to write full QCD Lagrangian. So let's call this QCD Lagrangian. So that will be the combination of, the kinetic energy term of the Lagrangian plus the Dirac term. Okay, let's write it. So QCD. First, if we write the kinetic energy term, so we can copy this and paste it here. Okay, so this highlighted part is the kinetic energy term. Yeah, I'm going uphill. Now I'm going to write this part of the QCD Lagrangian. So I'm going to write it in a proper way, because there is a sum on Q, because we have three colors, and there's sum on alpha, Q bar alpha iota gamma mu T mu minus M Q bar alpha minus 1/2 GS G mu A Q bar alpha lambda of A. I took the two outside of alpha beta gamma mu Q beta. Okay, so I have the complete QCD Lagrangian. The first term is purely kinetic energy term, and it describes 8 gluon fields. Okay, and then I have 3 gluon field interactions and 4 gluon field interactions, and then the Dirac free Lagrangian, and Q is sum over the flavors, and alpha beta is sum over the colors. And this term right here is the interaction of quarks and gluons. And so yeah, this Lagrangian is very rich. So gluons are also going to interact with themselves. Yeah, that's it.